Hi everyone, this is Mrs. Jackson. This is Chapter 2, Section 1, Part 2. In this video, we're going to be talking about the vertex form of a quadratic function, and we're going to use that form to graph a function and then identify key features. And in the bottom of the video, we are going to write the vertex form of a quadratic function when given the vertex. Okay, so first things first, I will write down the function form. Just to jog your memory, we've got some kind of stretch factor, and we have some kind of horizontal translation, and some kind of vertical translation. So in our particular example here, we've got a stretch factor of 1/2. It's positive. That means we'd expect an upward facing U, and it's got some vertical compression, meaning it's going to get a bit wider and shorter. We're adding 2 to our x variable. That means we're going left 2, and we're subtracting 3 from the output, which means we're going down 3. So I can read my vertex right off of the equation. I've got a vertex of -2, -3. It is upward facing, and we have a line of symmetry that's going to go straight through that x coordinate there, and our x coordinate on that vertex is -2, so our line of symmetry is going to be x equals -2. And domain and range, I'll save that for after we graph our function. We do have compression, as I already said. A is equal to 1/2. And I think we will also leave the y-intercept until after we graph. Okay, so let's move over here and start graphing. We have a vertex at -2, -3, and a line of symmetry, which I'm going to draw here in black, that's going to be at x equals -2. And how do we deal with this stretch factor? So with no stretch factor, I would be moving off of my vertex 1 unit and then square it for y equals x squared. So 1 squared would give me 1. So on our parent, we would expect on either side of this vertex to go up 1, and 2 squared would go up 4. 3 squared would go up 9. However, with a compression of 1/2, all of those numbers are going to be cut in half. So if I square 1, instead of, I'm going to have 1 out, but I have to multiply that by 1/2. So I'm going to have my wider graph, and of course I have symmetry, that's going to push it down, which is going to make it look wider. If I move over 2 units now off that vertex, 2 units, if I square 2, that gives me 4 units, but I have to multiply that by 1/2 because of the stretch factor, so that would be 4 times 1/2 would give me 2. So I'm moving over 2 units and going up 2 units. If I square 3, I get 9, but I've got to chop that in half, so that means I'm going to be going up 4.5 units. So here's my x dimension, square that 3, I'm going to be going up 4.5. Right there. And so you can see, let's see, can I do another one? If I square 4, that would give me 16, and half of 16 would give me 8. Yeah, I could fit that in up here. So that's the way we use that stretch factor to determine where our points are going to be. All right, so now that we have our graph, let's finish up our key features. We can see here from our graph, the domain is unlimited. So you could write all real numbers, or a minimum of -infinity, maximum of +infinity. Our range does have a minimum, however, because of it being an upward facing parabola. So our minimum is going to be at -3, and we can touch it, and our maximum is going to be infinity. And finally, our y-intercept is y equals -1, or you can write that as a point, 0, -1. So that's how we would graph when given the function. Now let's take a look at how we can write a function when given the vertex information. And I should point out here that a good example to read in the textbook is on page 75, which is another example of how to do this. All right, so we're told that the vertex is -1, -4. That means we're going left 1. So if I start writing my function here, and I know maybe you guys are getting sick of f of x, so maybe I'll just keep it simple and say y equals, we have some kind of stretch, we have x, some kind of horizontal translation, and some kind of vertical translation. So that's our h and our k. We're moving left because we have a vertex at -1. That means we're going to see our x, add 1 here to go left, and we're also going down 4. So we're going to subtract 4 from our output. All right, so we're almost there. However, we don't know what the stretch factor is right here. But we're going to use a point on our function and calculate what that stretch factor is. So over here we can see that we have a y-intercept of 5. That means x is, so that's a point. So for our y-intercept, x is 0, and our y-intercept is 5. And I'm going to plug in that x equals 0 and y equals 5 into my function and actually calculate what a is. So I'm going to put 5 here, and I'm going to put my 0 in here for x, and I'm going to solve for a. So I have 5 equals, I have 1 squared, which is just 1a, and then I subtract my 4, solve for a, and I get a equal 9. And so just kind of pull it all together and write the final function. We've got y equals 9 x plus 1 squared minus 4 would be our final function. So that is quite a bit of stretch. It's going to be an upward facing U, very skinny and tall. Okay, next problem, we have a vertex information here. This is H and K. We're going left again. This time we're going up. So I'm going to start out with our stretch. And I'm going to substitute in x plus 3 since we're going left. And we're going up 7. And we're told that we have a point on our function at -2, -5. I'm going to substitute that in and solve for my stretch. So I have a times 1 squared, which is just 1, plus 7. And I end up with a equals -12. Bring it all together to your final function, and I've got y equals -12. Downward facing U, huge amount of stretch. Going left 3, going up 7, and that is our final function form. Okay, in this video, we learned how to take the vertex form, make a graph, and we learned how to take the vertex information and make an equation. I hope this helps. Thanks for listening.